Hello and welcome to the fourth and final video of the M3 chapter Circular Motion. Exam question on the screen to get us going. If you've got time, pause the video, have a go now. A light rod AB of length 2a has a particle P of mass m attached to B. The rod is rotating in a vertical plane about a fixed smooth horizontal axis through A. Given that the greatest tension in the rod, that happens at the lowest point, and that radius is 2a, the greatest tension in the rod is 9 mg over 8. Find to the nearest degree the angle between the rod and the downward vertical when the speed of p is that. So I'm going to look at this point first. Here we've got the weight acting this way, we'll have some velocity this way. This is my h equals 0 level here. So I'll call this B, and we're going to look at the total energy in the system. At B, we've got gravitational potential energy equal to 0 because of my h equals 0 level, and our kinetic energy is equal to half mv squared, and we can calculate what V is by looking at the tension here, because we know that tension must balance the weight and also provide for the circular motion. So our tension, 9 mg over 8 minus the weight, is our resultant force in our F equals ma equation. And mass times acceleration, we're going to have v squared over r as our form of acceleration. I know r is equal to 2a, and on the left 9/8 minus 8/8 is 1/8, so that's mg over 8 is equal to mv squared over 2a. Multiply that over and we get amg over 4 is equal to mv squared, and then I can take that mv squared back up into my kinetic energy and take half of that is the kinetic energy, so half of that is amg over 8. So with no gravitational potential energy, the total energy in the system is equal to amg over 8. That's energy. So when we look at another point on the circle, call this point C, as we're coming around, we know that that total energy must still be amg over 8. But now we've got gravitational potential energy, and that is equal to mass times gravity times the height, which, as I've drawn it, would be 2a plus 2a cos theta, but I don't know yet if that theta will be here as an acute angle or here as an obtuse angle, in which case I would probably give the acute angle there. So let's assume it's in blue here instead of this one, theta here. So my height is going to be 2a minus 2a cos theta. So we've got 2a and then 1 minus cos theta in brackets. And the kinetic energy, we're told the speed, so there's a half times m times v squared, which is ag over 20 when you square that root given in the question. So that's amg over 40. And this gravitational potential energy, 2amg 1 minus cos theta plus the amg over 40 for the kinetic energy must equal that total amg over 8 still. Now I can rearrange this. 1/8 minus 1/40 is 1/10. And we've got 2 amg 1 minus cos theta, squeeze that in there. amg's all cancel. That's great, so that's 1 over 20. 1 minus cos theta, so cos theta is 19 over 20, which gives me a theta of 18.19 ... and they want theta to the nearest degree, so theta is 18 degrees to the nearest degree, so we're right to use the acute angle here. In this section of the chapter we're doing almost the same thing, we're doing all of that, and then we're going to combine it with stuff we've looked at before, because we're going to look at objects that are not constrained to a circular path, which means that they will start on a circular path doing all that stuff we've just done in the starter, and then something will happen and then they will not be on the circular path anymore. Generally, what that means is they will then be moving freely under gravity. One situation is if a string goes slack. Once it goes slack, there's no tension left, the particle is now moving freely under gravity. Another situation is if it breaks. If a string breaks as the particle is moving around in a circle, then it will go flying off. The starting velocity will equal the velocity at the point when the string breaks. Then it's moving freely under gravity again, and you can treat it as a projectile using all of our projectile stuff that we did in M2. Another option, though, is something that we haven't looked at yet, and that's a particle moving on the outside of a sphere. Now, if you've got a sphere or a hemisphere, and the particle is at the top, say, and it's moving this way, or here's a hemisphere, again, particle on the top moving this way, initially it will be in contact with the surface. And because the surface here or here is a spherical, and therefore in a 2D sense circular surface, it will have circular motion. However, there will come a point where the particle leaves the surface and is starting to move under gravity. Same here, bad drawing on this one. But obviously the particle, unless it's somehow magnetically stuck on, it won't be able to continue round the surface of the sphere like this. It will have to leave the surface at some point. And when that happens, again, it will be moving freely under gravity as a projectile. The main difference between these is in this type we'll have tension in a string or a rod. In this type we've got the weight providing the circular motion, and the normal contact force will get smaller and smaller until it becomes zero when it leaves the surface. So we'll look at a couple of examples like this. But what we need is to review M2 Chapter 1 for motion of a projectile if you've forgotten any of that work, because we're going to be using those ideas in this section. That's it for the notes. On with some examples, quite involved examples, and an exam question to finish. So a particle P of mass m is attached to one end of a light inextensible string of length L. The other end of the string is attached to a fixed point O. The particle is hanging in equilibrium at point A, where A is directly below O, something like this. This is L, the particle is down at the bottom when it is set in motion with a horizontal speed 2 root GL. When OP is turned through an angle of theta, let's call that B, and the string is still taut, the tension in the string is T. Determine first an expression for T, then the height of P above A at the instant when the string goes slack. So this speed that's given initially is not enough to continue circular motion all the way round. It's going to go up a certain distance, and then at some point the tension will become zero, the string will become slack, and at that point the particle will be moving freely under gravity. Part C, the maximum height above A reached by P before it starts to fall to the ground again. Now that actually gives us a little clue, because we wouldn't have much work to do in that if it didn't get past 90 degrees, because if it didn't manage to get past 90 degrees, the string wouldn't actually go slack, it would just fall back down, but it would still follow this curved path. So most likely it's getting beyond that, so it's got upwards velocity, tangential velocity, so that when the string goes slack, it's still moving upwards slightly under gravity and then comes down like this. So that's an overview of the idea of the question. Part A is very similar to what we've already been doing. Find an expression for T. So this is very similar to what we've already done. We're going to say at A, the gravitational potential energy is equal to 0. That's my H equals 0 level. The kinetic energy we can work out is a half mv squared. And we know that this is V. So V squared is 4gl, divided by the 2 there is 2mgl. So our total energy is equal to 2mgl, and that doesn't change when it gets to B. At B, as we just said, that total doesn't change, that's 2mgl. Then our gravitational potential energy, mgh, is equal to mg times the height, which is L minus L cos theta. And then we've got our kinetic energy, which is a half mv squared, and the total energy minus the gravitational potential energy must equal the kinetic energy. Of course, to get an expression for t, we're going to need to resolve along the radial direction at b. So here we've got mg, so this way we've got mg cos theta, and using our F equals ma equation, the resultant force in towards the center is T minus mg cos theta is equal to m, and then we're going to use v squared over r, where r is equal to L. But we know what mv squared is. It's just 2 times this thing. So I'll just squeeze in the space here, multiplying everything by 2 here and here, expanding out this brackets. We're going to get 4 mgl minus 2 mgl. That will be 2 mgl. And then we're going to have plus 2 mgl cos theta. And that is equal to mv squared. Substituting that in here, 2 mgl plus 2 mgl cos theta, all divided by L, T minus mg cos theta. The L's cancel out. We get 2 mg cos theta plus another mg cos theta when I bring this over here. So we've got our 2 mg plus 3 mg cos theta is our expression for t. Part B is the height of P above A at the instant when the string goes slack. So we've got 2 mg plus 3 mg cos theta for t, and that is going to be equal to 0 when it goes slack. That gives us minus 2 mg over 3 mg for cosine theta, minus 2/3. That is about 131 degrees, which is telling us what we already knew. It started down here, and now it's up here somewhere. And when that goes slack, the question is, how high is that above A? That means the vertical height from here to here. And this is theta. So our height, as we said before, is L minus L cos theta, and cos theta we now know is minus 2/3. So call this H. So it's L plus 2/3 of L, which is 5/3 of L. And that is the height above A at the instant when it goes slack. Part C then continues this. What is the maximum height above A reached by P before it starts to fall to the ground again? So as mentioned before, this is where it goes slack, but that doesn't mean it suddenly falls or goes back this way, because it's moving in this direction, tangential velocity. So it's going like this. It continues up a little bit, not at the full extension of the string, but in a little bit and up a little bit before it then starts to come down like this. So there is a motion, let me put it on here, something like this. And the question is, what is this maximum height here? Before we continue on though, what I'm going to do, because of what we're going to talk about in a second, I'm going to just make note that if I use this angle here, call that alpha, then the cos of alpha is equal to a positive 2/3. This is the acute value rather than the obtuse value. The reason I'm going to use that 2/3 is because we're going to be splitting this tangential velocity into its component parts, because we don't normally want a tangential velocity if we're talking about projectile motion, especially if we want to find the highest point. We know that happens when the vertical velocity is 0. So we're going to want the components here. I don't really want to be working with an obtuse angle. Quick bit of parallel lines in here tells us that the V here gives us a V sine alpha vertically and a V cos alpha horizontally. Now a second thing that I'm going to do before we even start part C is to get an exact value for sine of alpha. Now you don't have to do this, you can work with decimals, but seeing as we've got 2/3 for cos, if I look in my little right angle triangle here, if this is alpha and cosine is adjacent over hypotenuse, then this is hypotenuse squared, that's 9, minus 2 squared is 4, that's 5, square root of that. So the opposite side is root 5, so the sine of alpha is opposite over hypotenuse. And that will just help me keep exact values as we go through the next part. So writing down the things we know. We're going to start here, it's moving this way. We've got V going this way, but we know that this is V sine alpha, which I just said is root 5 over 3 of V. V going this way is V cos of alpha, which is 2/3 of V. So we've got our velocity split into its components, but we also know what V is. If we go back to the expression over here, we can work out V because we know cos theta, so that's 2 mgl plus 2 mgl cos theta equals mv squared. Cancel those. I'm back to using cos theta, so this is negative 2/3, so that's negative 4/3 gl, 2gl equals v squared, which gives us 2/3 of gl for v squared, so v is equal to the root of 2gl over 3. Now we're in a position to apply constant acceleration formulae. Considering the point here as our start point, we know the initial vertical speed is root 5 over 3 times this. The vertical speed at the highest point is 0, and we know the acceleration is due to gravity alone. So I'm going to do that over here with the upwards direction as my positive. So u is equal to root 5 over 3 times root 2gl over 3. My final vertical speed is 0. Acceleration is due to gravity, but it's down, so that's negative g. And s is the thing I don't know and want to know, so we're going to use v squared equals u squared plus 2as, or s equals v squared minus u squared divided by 2a. So that's 0 minus u squared, that's good, we get rid of some of these square roots. That gives me 10gl over 27, all divided by 2 times minus g. The g's cancel, the minuses cancel, we get 5 over 27 lots of L for the distance from here to here, the vertical distance. But we need to add that on because we want the height reached by P above A, and A was at the ground level. So we need to go back, we've got 5/3 of L already up to this point. So the total height is 5/3 of L plus this extra little bit moving under gravity gives us 50 over 27 L as our final answer for this part of the question. You could have done this from an energy point of view, which it does in the book, because you know at this top point the only speed is the horizontal, so you can use that to find the kinetic energy. Take that away from the total energy in the system, which we had earlier in the question, and then equate what's left with mgh to get the height. I prefer considering constant acceleration formulae because I think it's a little bit more versatile for the different types of questions you might get asked, as we'll see in the next example. Here we've got a smooth hemisphere, radius 5, center O resting on a fixed position, horizontal plane. The flat face is in contact with the plane, so it looks kind of like this, with O here. Particle P of mass 4 kilograms, slightly disturbed from rest at the highest point. So up here, where initially it's got no speed, but it does have a mass so the weight is 4g, and we know the radius as well is 5. When OP is turned through an angle of theta, the particle is still on the surface of the hemisphere. The normal reaction, which of course acts radially outward, is r. We still have mg here, and the difference to what we've done before in this situation is that we don't have a tension. The circular motion from here to here, that is being provided by the weight acting radially inward. Of course, as it comes round, that becomes a component of the weight, and so the reaction force gets less and less until it leaves the surface of the sphere or hemisphere, in which case at the point it leaves, r is 0, but I'm getting ahead of myself. The first question is just to determine an expression for r. So I'm going to bring this little diagram with me, and we're going to find an expression for r by doing very similar things to what we've done before. Call this A, call this B. At A, considering the energy, we've got gravitational potential energy is equal to mass, which we know in this case, times gravity times height, which we also know. So that's 20g, and the kinetic energy is 0 initially. So our total energy in the system is just 20g. At B, we've got a reduced height, so the gravitational potential energy is now 4 times g times 5 cos theta, where this little angle in here is theta, and the kinetic energy is equal to half mv squared. So if we take that total 20g and we take away the gravitational potential energy 20g cos theta, that has to equal half mv squared, except we know what m is. That's a 4, half of 4 is 2v squared. Now to figure out an expression for r, although we don't have tension, we're still doing the same thing. We're going to resolve along the radial direction here. Inwards, providing the force for circular motion, is the component of the weight, so we've got mg cos theta minus r, and that has to equal ma. Mg cos theta minus r is equal to mass times v squared over r. We know what m is, so that's 4g cos theta minus r is equal to 4v squared over 5. Combining these two, we've got 2v squared here, so if I double this and drop it in here, then we get 40g minus 40g cos theta, all divided by 5, 4g cos theta minus r, so that's 8 on the right. We bring that over, we get r is equal to 4g cos theta plus 8g cos theta is 12g cos theta minus 8g, and that's our expression for r. Similar to the previous example, we now need to find where that is equal to 0, the angle between OP and the upward vertical when the particle leaves the surface of the hemisphere. In our previous question, this is when the string went slack, t was equal to 0, but here where it leaves the surface of the hemisphere, the normal reaction force disappears. So effectively we're asking, when is this expression equal to 0? So that r is equal to 12g cos theta minus 8g, and that has to equal 0. Quick bit of rearranging gives us our answer. Get rid of those. We've got 2/3, same as the previous example. We didn't get round to actually writing down this number though, and that is 48.189 dot dot dot. 48.2 degrees to 1 decimal place. That's part B. On to part C. The distance of the particle from the center of the hemisphere when it hits the ground. So if we take the point in the diagram here as the point where it leaves the hemisphere, then it travels freely under gravity and is going to hit the ground somewhere over here, a little bit further out than the radius. So what we need to do, we need to take the distance here, which we can figure out quite easily, to this point, then add on the horizontal distance it travels while moving under gravity. To do that, we need to know the horizontal speed. That's not too bad. But we also need to know how long does it travel at that speed. To figure out that, we need to know how long does it take to drop from here down to the ground. So let me put on here, we've got an initial velocity in this direction. If this is our theta here, then that is here. So our horizontal velocity, v cosine theta, which we know is 2/3, and our downward velocity here is equal to v sine of theta, which, because the numbers are the same as the previous example, we know is √5/3. That's convenient, we don't need to figure that out again. But what is v? To find v, same as in the previous example, I go back to the expression in part A, and we can put in cos theta is 2/3. So we've got 2v squared is equal to 20g minus 20g cos theta, 20g minus 2/3 of this, 40g/3, and I can divide everything by 2, and that all gives me 10g/3. So v is equal to the root of 10g/3. So we know v, we know the downward speed initially here, and the horizontal speed, which doesn't change as it moves under gravity. We'll use that later. But first I need to know what is the time it takes to go from here down to the ground. So again, over here in yellow, I'm going to take down to be positive this time. Our initial speed vertically is √5/3 times √10g/3. We don't know the final velocity when it hits the ground, but we do know the distance, and that is 5 cosine theta. That's 10/3 because cos theta is still 2/3. We also know acceleration is due to gravity in a downwards direction, and we want to know the time. So here we've got s is equal to ut plus 1/2 at squared, and we get to solve the quadratic equation. So 10/3 is equal to this horrible thing here, √5/3 times √10g/3, t plus 1/2 of g t squared. I'm not even going to pretend to try and keep this in exact form or to do the work of solving it. I'm just going to throw all of this on my calculator and find out what is t. And according to my calculator, that gives me a time of 0.4976 ... or a negative 1.36, which of course we're not going to use. Now we know the time it takes for the particle to hit the ground. We're going to take that time and multiply it by the horizontal speed to give us the horizontal distance traveled in that time. So we've got the distance, or I'll call it the extra distance, is equal to 2/3 of v, and again v is this horrible thing here, times time, and that gives me a decimal answer of 1.896 ... And I say extra distance there because we want the distance from the center of the hemisphere. So again, we've got this distance here, 5 sine of theta. So the total distance is 5 times the sine of theta, which we know is √5/3, plus this 1.896 extra distance gives me 5.622 ... And because I've used g as 9.8, I should round that to 2 significant figures. And that is the distance of the particle from the center of the hemisphere when it hits the ground. There's 2 fairly full-on examples there. Let's finish with an exam question. A smooth sphere of center O and radius A is fixed with its lowest point A on a horizontal floor. So this time we don't have a hemisphere, we've got a full sphere, but it is fixed on the floor. It doesn't roll about. This is my h = 0 level. It's got a radius of A. Particle P is placed on the surface of the sphere at the point B, where B is vertically above A, so that's right at the very top Here is B, here is A. The particle is projected horizontally, in this case not disturbed from rest, but with a speed, and that speed is root AG5. Moves along the surface of the sphere. When OP makes an angle theta with the upward vertical, and P is still in contact with the sphere, the speed of P is V. Show that this V here, or the V squared, is equal to this expression. And now we've done two examples. This should seem quite familiar now. What I'm going to do, I'm going to consider at B the energy in the system. We know the gravitational potential energy is equal to mass, which they haven't given us. That's unusual. Usually they give at least an m, let's call it m, times g times the height, which is 2a. And we do have kinetic energy, and that's a half times mass times v squared, which was given, that's mga over 10. So our total energy in the system is 2 mag plus a tenth mag, 21 mag over 10. Let's call this point here point C. At C, the gravitational potential energy is equal to mass times gravity times A plus A cos theta. If I write it like that, the kinetic energy, a half mv squared, and that's the v squared we're trying to calculate. And both of these have to add up again to give us that total energy, 21 over 10 mag minus the gravitational potential energy, mag minus mag cos theta is equal to a half mv squared. So that's 11 out of 10 mag minus mag cos theta equals a half mv squared, and we want v squared, multiply everything by 2, gives me 11 over 5 mag minus 2 mag cos theta. Cancel all the m's, and they want it in brackets, so we pull out ag over 5, and that gives us 11 minus 10 cos theta. That's good, that is what they want. That's the first question finished. Then it goes on to say the particle leaves the surface of the sphere at the point C. Okay, great, that's the point there. Let's assume this is where that happens. Find the speed of P at C in terms of A and G. So to find the speed of V, which is the expression we've got here, we need to know what is that angle. When does this happen? To find the angle, we're going to resolve radially. We've got mg here. That gives us mg cos theta in towards this and r coming out. So we've got our F equals ma again, and the resultant force mg cos theta in radially minus r is equal to mv squared over r, which we know is a. Then I'm going to substitute in mv squared, this expression here, for the mv squared here. That's equal to 11 over 5 mg. The a here cancels with this a and also with this a, so I won't write those. Minus 2 mg cos theta. Normally I would write that underneath rather than next to, but I'm running out of space. I want to squeeze it all on this screen. So rearranging this, we get 3 mg cos theta minus 11 over 5 mg and r on the other side. So r is equal to 3 mg cos theta minus 11 over 5 mg. And the key point here, when it leaves the surface of the sphere, that is when the normal contact force has become 0. So this equals 0, and then we can find cos theta because mg's cancel. We get 11 over 5 on this side and 3 cos theta. Cos theta is equal to 11 over 15, and theta is equal to 42.8 degrees. And I've just realized I've answered a question that they haven't asked. We didn't need theta, that's not what it wanted. It wanted the speed. So cos of theta is more useful. 11 over 15 we want to put back in here. We've got 11 minus 10 times 11 over 15, lots of ag over 5 for v squared. And if you tidy all of that up, you get 11 over 15 ag. So v is the square root of 11 ag over 15. So we've got the speed of p at that point where it leaves the surface. Now we want the size of the angle between the floor and the direction of motion of p at the instant immediately before it hits the floor. So what we're looking for here, as this leaves the surface, comes down here, hits the floor here, we want to know the direction, so we're going to need the vertical and the horizontal components of the speed to give us the direction it's going when it hits. Fairly similar to the previous example, we know v, so we can find the component of v. V is going this way initially. We've got v cosine theta here, and vertically v sine theta. Now cosine theta was 11 over 15 v, and that seems a long time ago now, but in the other example we did the little right angled triangle. We've got theta here, then the cosine is 11 over 15. A bit of Pythagoras tells me that this is the root of 104, so the sine is equal to the square root of 104 over 15, which simplifies to 2 root 26 over 15 v for our downward speed component. This time we don't need the time it takes, what we need is the final vertical velocity when it hits the ground. So looking at our constant acceleration formulae, our initial downward speed is that horrible thing I've just said, 2 root 26 over 15 times by v, which was 11 ag over 15 square root. Our acceleration is gravity downwards. We know the distance is a plus a cos theta, where again cos theta is 11 over 15, so that's 26 over 15a, and what we want to know is the final velocity as it hits the ground. V squared equals u squared plus 2as. I'm very happy that we're squaring u. That gets rid of all those square roots. That gives me the really horrible 1144 ag over 3375 plus 2 lots of a times s, which is 26 over 15a, which gives me a total of 12844 ag over 3375 for v squared. So v is the square root of that. Lovely number there. And that is our downward speed as it hits the ground. Horizontal speed as it hits the ground is still the same thing, 11 over 15 times v, which is 11 over 15 times the root of 11 ag over 15. So to get the angle it hits the floor, I want to take this, divide it by this, and then take the inverse tangent of that. So tan of theta is equal to the square root of 12844 ag over 3375 divided by, if I put all of that in the square root, I get 1331 ag over the same number 3375. Then I can combine those two fractions within a giant square root. The ags cancel, the 3375s cancel. We end up with the square root of 12844 over 1331. The inverse tan of that is equal to 72.155 ... to one decimal place, 72.2 degrees for theta. Now I realize I've used the same variable for different things in the same question. That's not a great practice. This v different to this v, this theta is different to this theta, but I hope you followed what I've done as I've talked through it. A lot of parts to this sort of question, but hopefully if it comes up in an exam, it will be a very similar process. That should be enough now for you to have a go at exercise 4E for this particular section, and then the chapter 4 review exercise for this whole chapter on circular motion.